three-dimensional representation of forces and moments brings with it a lot more than just one simple additional dimension, particularly when we try to conceptualize and understand physically what's happening. And so one of the key things in describing a force or any vector quantity in three dimensions is understanding how it's oriented. So at the point of application of the force is, say, at point 0, then the way that we represent the orientation of the force in three-dimensional space is by angles, or direction angles we call them, from the respective three axes. And alpha by convention is usually what we use as the direction angle measured positive from the positive x-axis to the vector. Whether that's a position vector or a force vector or moment vector, doesn't matter. It's going to be positive from the x-axis to the vector of interest. Right? Our beta, or vita in more correct Greek pronunciation, would be the direction angle from the positive y-axis to the vector. And then finally we'd have our gamma, which would be our direction angle from the positive z-axis to the vector of interest. And note that you can end up with then angles that vary from 0 to 360 degrees. Right? So swinging all the way around and measured in a sense in a positive way, but boy, what's positive is a lot more confusing than in the two-dimensional space. But it would be positive in your typical counterclockwise kind of fashion from the respective axis. And that's a little bit of a confusing kind of thing of, wait a minute, what really is positive? And that's where we end up with looking at direction cosines. And so we can swing this in the sense of what is positive and negative in the following kind of way, that this vector u can be thought of as a cosine of alpha times unit vector I plus cosine beta unit vector j plus cosine gamma unit vector k. Right? And so if alpha can swing from 0 to 360, then cosine can swing from 1 all the way to -1 and then back as we go around in the full circle. Right? So what counts as alpha as positive, you can start to begin to think of in that kind of context. So if we go back to this unit vector here that you've got showing, then our cosine alpha would be associated with going out to here. Right? And then notice that's also the same as this part of this little box. And then cosine of beta is effectively giving us that kind of a value. And then cosine of gamma is that little portion that is sticking up. And of course you can translate that over and put it right on the respective axes as well. And note that in this special kind of case here, when we look at the magnitude of u, we get square root of cosine squared alpha plus cosine squared beta plus cosine squared gamma. And that total magnitude will be exactly equal to 1. And whether it is a force or a moment vector, that's how we represent the directional aspects of it. And then when you get to the actual version of f, or any force vector, notice it'll have an x component plus a y component plus a z component, and the fx itself then will be equal to the magnitude of f times cosine alpha, and etc. for all the rest of them in their respective fashions, such that you can write f as equal to its scalar magnitude times that unit vector f, assuming of course that then our f is going on like so. And we turn that into a moment just simply by talking about it in the terms of moment equals scalar x component plus scalar y component plus scalar z component.